Welcome to part 3 of stability and cloud development. Once again, this is in chapter 6 for ESCI 211. All right, so what should we remember from this part of the online lecture? What you want to know: what is a conditionally stable atmosphere? What is the cause of an unstable atmosphere, or what are the causes, I should say, of an unstable atmosphere? And the 4 causes of cloud development. Okay, so a conditionally unstable atmosphere is this. So we've got our blue dry adiabatic rate and our red moist adiabatic rate. And if the environmental lapse rate is right in between them, you get what is conditionally stable. Why is it called conditionally stable? Well, if we look at this altitude right here, if we bring an air parcel up that starts at 30 degrees, that are of these two conditions, either unsaturated or saturated, you'll notice that the saturated air parcel will get a temperature somewhere around 21, 22 degrees. But the unsaturated air parcel is going to have an air temperature of about 15 degrees. Now, what makes that important? Well, if you look at the environmental lapse rate, okay, so if you look at this, you see the saturated air parcel is going to be warmer than the environment. Okay, it's going to be at a warmer temperature than the environment, so that means it's going to keep rising. Now, if you look at the unsaturated air parcel, it's going to be colder than the environment. So the unsaturated air parcel is stable, while the saturated air parcel is unstable. This is why it's called conditionally stable. It depends on what the air parcel is like when we lift it up. Okay, so what is a conditionally unstable atmosphere? Basically, an unsaturated air parcel will rise and cool. Then when it's cooled, it will be colder than the surroundings and will come back down. So it's considered stable. But a saturated air parcel will be the opposite. When it rises and cools, but it will be warmer than the surrounding air. And that'll keep rising, so the saturated air parcel is unstable. So this is what conditional means. Okay, how can we cause instabilities? Number 1, air aloft is cooled. Number 2, the surface air is warmed. Either one of these will cause instabilities. So let's think about this. How could we cool the air aloft? Well, we could use winds to bring in cold air, or the clouds or air emit infrared radiation to space, and we call this radiational cooling. So let's think about the other way. How could we warm the air the air at the surface? Well, we could have solar heating of the surface. That definitely will warm the air right above the surface. We could bring in warm advection or warm winds, or we can move the air over a warm surface. These are all ways to cause instability. All right, some other ways. Another cause is mixing or lifting of the air. So let's look at mixing. So if we mix the air, basically we have surface air, which is warmer air, and it is raised and adiabatically cooled. The air aloft which is colder air, could be lowered, and it would be adiabatically warmed. This could be caused by convection is one, or wind. And so what happens is you get a change in the environmental lapse rate. it is changed from a stable environment to an unstable environment. How can this happen? Well, temperature at the top of the air layer could cool, while the temperature at the bottom of the air layer will warm. Here, let me show you a graph example. All right, so this purple line here is the environmental lapse rate before mixing, and that's closer to the moist, so this would be to be stable. Right? Now we mix everything together and we get this new environmental lapse rate. Now that one is more akin to the dry adiabatic rate, and it looks to me to be a little bit lower, so now we have an unstable atmosphere. Okay, another cause for instability is lifting. So somehow we lift the air. So we can have a change in the environmental lapse rate. It is changed from stable to unstable to a conditionally unstable condition. That's one. Can happen lifting. So what we can have is an unsaturated layer of air is lifted into a region of less pressure. The air will expand and it will increase in thickness. This will cause the top layer to cool more than the bottom layer. Okay, so here's an example of that. Here's our bottom layer. Here's our top layer. And as we raise the air up higher, right, you see that the bottom cooled a little, but the top air expanded even more, and it cooled even more. So now the top is cooler than the bottom. Another cause for instability is what's called a convective instability. Well, what is that? That is when you have a layer of air is saturated on the bottom, but unsaturated on top. So as this is lifted, the top and bottom cool at different rates. The top cools faster at the dry adiabatic rate compared to the bottom's moist adiabatic rate. Sooner or later, as the air is lifted, the top will become cooler than the bottom. So let's look at an example. This. So here we go. Here's our air on the bottom, and you see now here the bottom is definitely cooler than the air on the top. Now we lift this, but the bottom is moist. Oh, sorry, the bottom is moist, so it cools at only 6 degrees for every 1,000 meters it goes up. And the top is dry, and that cools as 10 degrees as it goes up. And you definitely see that the air at the top now is cooler than the air at the bottom. And we have warm air on the bottom, cold air on the top. And that's a stable atmosphere. All right, so how can these atmospheres give us cloud development? Okay, so how does this affect clouds, or the development of clouds is the question. Well, it's pretty straightforward. To form a cloud, air has to rise, expand, and cool. So to do this, there are 4 general mechanisms to do this. We can have surface heating that will initiate convection. The air will rise, expand, and cool. Clouds could form. You could have topography cause the lifting, so mountains or coastlines. You could have widespread ascent due to convergence of surface air. So once you imagine all the air at the surface heading to the same location, well, that air's got to go somewhere. It can't just keep heading in the direction it has. So what happens is it heads up and it pushes the air up. and that's lifting, and that can cool the air as it goes higher. And then the last thing is uplifting from weather fronts. If you have a mass of cold air meet a mass of warm air, cold air is more dense than the warm air. The cold air will push the warm air up. Again, we have lifting. So let's talk about this surface heating and convection. So we're going to simplify our models, and the simplifications we're going to use is following. No mixing takes place as the air rises with its surroundings. No mixing between the air in the parcel and the air in the surroundings. Only a single thermal produces the cumulus clouds. So not two thermals, just one. Or only one column of rising air produces one cumulus cloud. And clouds will form when the relative humidity in the air parcel reaches 100%, or when the air temperature in the parcel reaches the dew point temperature. The air rises in the cloud, the rising air in the cloud remains saturated. So if when the cloud forms, we have saturated air, and that can keep, when it rises, it still remains saturated. Okay. Concepts about cloud development. One's called the condensation level. That is the elevation in which the cloud starts to form. There's another process that can happen when clouds form. There can be mixing of the warm and cool air on the boundaries of clouds, and that can also affect the cloud development, and they call this mixing entrainment. All right, let's talk about how topology can affect cloud development. Basically, it's called orthographic lift, and so if the air is blowing along the surface and it reaches an obstacle, so let's say a mountain, the mountain's going to force that air up, and so it's going to be pushed into less pressure, so it will expand and cool, and we can have clouds. Coastal regions can do the same thing. Air will be blowing along the surface of the water. Land is higher than the water, so the land will push the air up. This effect can produce something called rain shadows. That is, as the air rises up the mountain, the clouds will form, the air will become saturated, and then if we get enough saturation, we can have precipitation fall. And so this usually happens on the leeward side of the mountain, so that those sides of the mountains will usually get quite a bit of rainfall, or are the wettest places on Earth. And then since all the water is, say, condensed out of the air as the air goes up the mountains, so on the other side of the mountain you get what is referred to as the rain shadow, where since all the water is pushed out, you have very little precipitation on that side. So in the U.S., it's a difference between California on the western side of the Rockies and Colorado, New Mexico, and Nevada on the eastern side of the Rocky Mountains. Just think about those areas. Which one has the most water? Okay, so lifting condensation level, another term here. This is the level where we have the base of the clouds forming in the air, and that happens when the air is reaches saturation. This happens when the dew point temperature reaches the air particle temperature of the parcel. All right, so at this point, when the cloud is formed, the air, is it going to be saturated or unsaturated? Well, since the cloud is formed, we have condensation. So that means we have moist, saturated air. So which lapse rate should we be using? We should be using the moist adiabatic rate at that point until the air is cool enough, the parcel of air is cool enough that it matches the environmental lapse rate temperature, and then it won't rise anymore. All right, so what should we remember about this online lecture? Well, you should remember what the definition of a conditionally stable atmosphere, what causes an unstable atmosphere, and the 4 causes for cloud development. Okay, I believe this ends the chapter on stability, and I'll talk to you later. Bye.